Okay, hello everyone. Welcome to lecture 32, I believe, of GPU mode. Today, I'm really thrilled that we have the Han brothers, Daniel and Mike, here to talk to us about Unsloth. I think the first time I'd heard about you guys was for the NeurIPS LM efficiency competition from last year. Y'all were doing already some really cool stuff and some very sort of precise performance work. And it's kind of been very obvious to me meeting both of you that you both really love what you do. So your enthusiasm is pretty infectious. So I'm really glad you're here in the server. So yeah, if y'all throughout the chat, throughout the talk, if you have any questions, please post them in the Q&A here on Zoom, and we'll occasionally read them out to Daniel. So thank you. Yeah, Daniel, please take it away.
Yeah, thanks, Mark, for thanking, and thanks to everyone. And the GPU mode 7, it used to be CUDA mode, but yes. Yeah, we started off with the LLM efficiency challenge way back last year. And then yeah, so we did Unsloth as a side project. Yeah, okay, I'll share my screen. Can you guys see that? Is that press slideshow?
Yeah, we see it. It's not in slideshow show yet, but we just see. Yeah, it's good now.
Okay, cool. So I was thinking, what should I talk about today? It was gonna be about Triton, CUDA, everything. So there will be half of the talk will be about that. But then I also wanted to talk about general systems engineering. Because when we first started Unsloth, it was we firstly made it as an optimization library, making fine-tuning faster, reducing memory usage. But we did not expect all the extra stuff that came with it, such as fixing bugs in models and stuff like that. So some of you might know me from Twitter as well. So we fix bugs, for example, in Gemma. So me and my brother, it's currently just 2 people in the startup, but essentially we fix bugs in Gemma. There was some BOS token issues, some rope issues, layer norm issues, Swiggloo, yeah, and just activation function issues. Also, we do model analysis as well. So for example, Grok, we post these. I don't know if you guys see this, but we post these stacked, fully packed paint images. So I use paint to do all these analysis. It's very fun. Sometimes it can get a bit tough and confusing when the model architecture is very different. And sometimes they do mistakes as well. For example, in Grok, I think I did a mistake with the I think the tan-H part. I think I did division, but it was actually supposed to be multiplication. So yeah, there are some mistakes in my model analysis as well, but it's fun. Also, for example, NVIDIA's Nemotron, 340 billion, I did some analysis on that. And also tokenization issues. There's a lot of tokenization problems in language models. So that's also very fun to provide to the community as well. And recently, if you guys have been following, there was a gradient accumulation bug. And so we showed that, so someone else, so Benjamin posted about the bug, I think 1 week ago or something. And this bug has been in most trainers for 4 years. And essentially the gradient accumulation was theorized to be equivalent to full batch training, but it actually wasn't. And I will talk about that today as well. Mainly, so Joey posted about a very cool picture showcasing the main issue of gradient accumulation. Mainly the denominator was not correct in the cross entropy loss calculation. And yeah, so we have a GitHub package as well. So we post all our fine-tuning, our fixes, our bug fixes, CUDA kernels. Well, we use Triton actually. We Triton kernels all in our GitHub package as well. So definitely check that out. Yeah. So yeah, in terms of a backstory, we firstly started Unsloth as with Triton kernels, some maths. We have our own backpropagation engine, and the goal at the beginning was to make LLM fine-tuning like Llama, Mistral, Gemma. Actually, it was just Llama. It was just Llama 2 fine-tuning 2 times faster at the very start. So this was around December, and this was launched after the LLM efficiency challenge, and we reduced VRAM usage by 70%. That was at the beginning. But we do not know that there is actually lots of extra stuff that you have to put together with the package in order to make it work. So I'll be talking about most of these things. For example, tokenizer problems, pre-trained model issues, exporting models to VLLM, collaborations of different entities and companies and organizations, making inference better, doing fine-tuning, DPO, ORPO, best practices for Lora, and also like many algorithms, chunked cross entropy, long context fine tuning, chain matrix multiplication, training on completions, and the gradient accumulation bug fix. So yeah, the goal is like, it's not just about making the Triton kernels better and, you know, writing optimized libraries. That's actually very important. But that was actually just the beginning of making like a full-fledged training library. And yes, there's some bugs and issues in every single one. So that was the unexpected part. So yeah, so like we essentially have to like notice, okay, even if you make like, you know, like implement, for example, we did not support Mistral models back when we firstly started. So, you know, we have to support Mistral models of sliding window attention. And then Gemma came along and there was like interleaved sliding window attention and like global attention. So that was like another new thing. And so like, there's always like these new things that come out. And so we have to implement them in Unsloth. Yeah, so it was very interesting. Like all of these parts of the stack kind of had like bugs and issues. Yeah, so going back to like our first release, essentially we took the transformer architecture, like the decoder llama style transformer architecture, and we like essentially like wrote it down in like all of maths, you know, just try to like make it as like into like one page of maths. And then we noticed like, okay, we could like Tritonize every single operation, you know, like do some back propagation tricks, like, you know, doing gradients, derive all the gradients, do calculus, do matrix calculus, and then like we essentially like make the entire process fully Triton. So our theory was, okay, this will make training somewhat faster and reduce memory usage. So for example, the RMS layer norm kernel that we wrote, it's cited in many packages as well. We posted so these kernels were like our beginning kernels that we posted around December sometime. We worked with them around like November, December, October, during the LLM efficiency challenge as well. And we like perfected them and like released them around December, I think December 1. I can't remember the release date, but yeah, so these are RMS layer norm kernels. You can see that we commented out, you know, some of these like upcasting and downcasting things. This is actually through trial and error that we did, especially like the backward kernels. We had to like upcast everything to float 32. We actually spent a lot of time and energy trying to like exactly, you know, copy the exact methodologies of like the correct gradients and the correct upcasting and downcasting. It's actually very painful because like, for example, the RMS layer norm kernel, there's like not that much casting and downcasting to do, but the other kernels you will see it gets more complicated.
So that's a quick question. Like I've been recently like sort of doing like a GitHub scan of like Triton kernels that exist, and I feel like RMS norm is like by far the most popular Triton kernel on the internet. Do you have some sense as to like why, like relative to all the other kernels people could possibly write?
That's a great question. I think RMS layer norm is like the first kernel, probably is like not that complicated, but not that easy. So it's like medium difficulty. You don't need to do like some interesting, there's not that much maths that you have to do. For the like derivative for the backprop part, it's not that complicated to derive the derivative. So my view is like RMS layer norm is like the first kernel people will try. That is like not that easy. Like, you know, addition is going to be very easy, but I think it's the difficulty level is reasonable for people to like try it out. That's my view. If that answers the question, yeah.
It does, yeah. Thank you.
Does Raid have a question? Is it?
It's okay. Like I think it's gonna be hard for us to do hand raises. So Raid, if you have a question, just post it in chat, and we can do like a cute live answers near the end.
But yeah, I will do Q&A. Yeah. Okay. So the next kernel that we did was like rope embeddings. This is actually more involved. The main reason why the rope embeddings was more involved is because now you have to like actually derive the derivative, and it was actually unclear what the derivative was. And so we did like some maths, and we noticed that, you know, in Llama, they use a function called rotate half. Rotate half might sound confusing, but like essentially they're like divided the tensor into two, they moved the right tensor to the left, they moved the left tensor to the right, and then they put a like, you know, minus sign and stuff like that. And it's interesting. And so like so the derivative was complicated. And then we noticed that actually it's just a rotation matrix. And if you do the transpose, it's just literally just transpose it. And just the transpose is just, you just put a negative sign. And so like, that was interesting. And so you can see like, for example, this line, if backward pass, it's just sign is equal to minus sign. So like essentially the most hardest part of it was like deriving the derivatives. The rest is actually not that hard. I think there are like some implementations of rope kernel, which is like they don't actually know that the layout of the kernels was the most important. And so like we essentially like wrote a kernel, which are like essentially considers the layout of the matrix multiplications as well. And so like you don't need to the multiplications, not matrix multiplications, but like you don't need to like, write a very complicated kernel if you just consider that, okay, if you draw on a piece of paper a layout of the rope kernel, when you do the actual multiplications, you can actually see that you don't actually need to complicatedly write the kernel and just like step by step, write all of these lines of code. So when we write kernels, you have to like write them on the piece of paper, and you will see that, okay, it's not as complicated as people think. Yeah. The next thing, it's not really Triton kernels, but like we do have like a, efficient flash attention inside of our package. One of the fundamental problems, though, is we had to use 3 different implementations of flash attention. This was launched back in December, though, so that's probably why. Now, I think people will, I guess you can just use scale.product attention from PyTorch. I think, yeah, PyTorch 2.5 just had the, Hopper architecture much faster. So like, yeah, I would suggest people to just use PyTorch's version. But, once when we launched back in December, we had to like include 3 different implementations, one from Xformers, one from the actual flash attention repo from TrueDAO, and like the actual PyTorch scale.product attention. And we're going to implement flex attention as well into Unsloth. But one of the problems was we couldn't use flash attention because the Tesla T4 GPUs did not have bfloat16 support. And so also scale.product attention did not have bfloat16 support during December. And so like we had to use Xformers as a temporary measure in order to support float16, flash attention on GPUs. So that was one of the reasons why we had to use Xformers. Yeah. Like Tritonized, it was with Llama, but Gemma has like Geglu and like other things. But like at the very beginning, Swiglu, it was okay to write down the derivatives and do all the differentiation. It was okay. But I think the biggest problem was, again, the casting and the downcasting. So like you can see, like, okay, why did we comment out DW's upcast, right? E has like an upcast. G, we had to like comment out the upcast. And so like this was like we used many ways to like check out the accuracy of all the kernels. And so like this is actually the correct way to do it. We now we can like utilize, like when you torch compile, you can like generate Triton kernels, and that's much more helpful, right? You don't have to like manually test which one is the correct method. You can like generate the Triton kernels and look which upcast is correct. So that's how we normally do it now. No more like pain of like trying to try every single combination. We also released cross entropy loss kernels. The code is a bit like combined together, so like I could screenshot it. But the cross entropy loss was very interesting as well. It was mainly about like you have to understand the maths behind it, like how do I actually derive the derivatives? How do I like do this efficiently? And so like we provided some of this in Triton kernels. During like when new models got released, we had to like add soft capping, logit soft capping through Gemma. We added like logit scaling for the cohere model, so we had to like edit the cross entropy loss kernels to make those work as well. We also like one of the biggest importance was like we moved the casting of like the linear layer for like float. Like when you do x times w, like the LM head, you have to like upcast it to float 32. Instead, you can like move it into the actual cross entropy loss kernel to like reduce memory usage dramatically. So logits, you just cast it dynamically inside the actual kernel. So like now I'm going to move over to like pre-trained models. So there's many models that got released: Llama, Mistral, Gemma, Phi, Quen, cohere models, many models from different companies and organizations. One of the things that we found was there's lots of bugs in them. And it's not really the model creator's fault. I would say that when you do pre-training of a large model, there's always going to be issues because the organization that like created the model is very large and big. And so like, there's always going to be some sort of issue that can't be like solved with like, the whole organization. You have to like have like one person to look through the whole code base and look through the whole system to see like if there are any issues. So like, for example, like Gemma, we found this was actually our first bug fix that we ever did to like support Gemma. And we found that actually Gemma had like some issues with their using the approximate value. And you're supposed to use approximate value, not exact. And for example, like also we found a rope fix at the same time. And so like rope was not done in float 32, and it was actually done in beat float 16 and float 16. And we found that actually Llama, Gemma implementations should not use lower precision rope kernels. If you do that, then you will lose accuracy at long context fine tuning. So definitely do not do that. So yeah, we posted like around 7 or 8 bug fixes for Gemma. This is around like March this year. Quite a while back. Yeah.
So Dan,
Yeah.
I'm sure like a lot of people have been curious about asking you, like, these seem like, I mean, the way to solve these would be like a guess, and I'm sort of curious how you went about like finding these in the first place.
Yeah, that's a great question. I think it's interesting. So like the first thing you have to do is like you have to read the code base for, when they release like a model implementation, we just take like a skim through it. Like, okay, is there anything interesting in this model architecture? So like that's why we do like these model analysis. Like, we also analyze models and then we like post them. And so like once you go through the analysis, you're like, wait a second, why is this like line over here? Like, why is it like, for example, why is the keras implementation approximate is equal to true, but then the PyTorch implementation approximate is false? Like, why is it like that? And so like we essentially read every single implementation that the companies or like transformers or any single organization launches, and then we compare all the implementations. And then when we like compare side by side these implementations, we see that, okay, they're not, why is this line like different from the other one? And so like after you do all these analysis, and then we like write up a correct version. So we actually have to hypothesize this is the correct version. And then we like, once you like hypothesize that this is the correct version, we then test, okay, like, is there like errors? Like, what is the L2 norm between each implementation? And so like, it is a long process, but in general, if you can like read through different implementations and like see which line is like wrong, you will then like find all these bugs. So it's actually not that complicated. I think it's like once you get used to reading lots of code transformers, you will see these little issues.
Yeah, like it's I think like, yeah, the search space is bounded. I think it's interesting. Okay, so there's like one long question in the Q&A. I think it might be best if you read it instead of me. So maybe let's just go over that one.
Okay, let me get my. How do I? Oh, that's a Q&A. Okay, it's in the chat. Oh wait, it's in the Q&A. Wait.
Okay, maybe let me just read it for you then.
Okay. Oh yeah. I'm a bit confused about this partial upcasting inside kernel. So if you upcast only one of the 2 operands, I'm pretty sure the compiler will automatically invoke an upcast anyway. Oh, yes. Okay. Interesting point. So sometimes if you upcast or downcast, it's fine. But sometimes the operations don't actually work. So I think like, so for example, if you go back to the, let's go back to the thing. Where is it? Yeah, right. Yeah, so for example, if you upcast and down, for example, this one, right? Because they were originally in float 16, right? So they're originally in B float 16 or float 16 because we're using mixed precision training. All of these like tensor, all of these like, things are in float 16, B float 16, right? So like you have to manually upcast them to float 32. For example, sigmoid is fine, right? Sigmoid, you must upcast to float 32 because there's no operation to exist in float 16. So actually, I'm not sure if like new Triton versions, but like you must upcast this to float 32. I think otherwise your Triton kernel will crash. I'm not 100% sure, but like you must upcast it to float 32. But I think the other ones, general matrix, general multiplications, it's not actually in the float 32. So you have to actually force the Triton compiler to tell them, okay, you must upcast this or downcast this, right? So like some of them we don't actually upcast. So the main point is like during the kernel, because we're using mixed precision, all of the tensors are in float 16 or B float 16, and so you must upcast manually float 32. If that answers the question. Continuing on. Okay, here. So when Llama got released, it was also very interesting. This was around April. I'm not sure you guys remember Llama. I thought it was just April. But that was very cool. We also found some issues in it as well. For example, like we noticed that so there's like a base model and there's an instruct model. We noticed that the base model actually had untrained tokens. So the Llama team probably accidentally set some tokens to like 0. So during fine tuning, it's probably not a good idea to set tokens to 0 because like some people, when you do fine tuning, the fine tuners actually don't know that some tokens are 0. And so sometimes what people do, they shouldn't actually do this. It's more like a user error. It's like they use the base model and then they use the Llama 3 chat template to fine tune the base model. And so we noticed that actually you're not allowed to do that because the EOT, like the end of turn tokens, the start header tokens are actually all 0 in the actual base model. And so if you do that, your gradients will become NaN. So don't do that. And so like for example, in Unsloth, we actually warn the user, actually we error out, we just error out. And we tell the user that, okay, if you're using the Llama 3 template on the base model, you will get NaN gradients. So definitely do not do that. Yeah, so we also like provide like a check for all models now. So if there's like a Llama, Mistral, Gemma, Phi, any single pre-trained model, we now check internally in Unsloth that, you're using like, these untrained tokens, please do not do this. Yeah, so this is not a problem just for Llama. It's actually a problem for many pre-trained models. When Phi got released, there was also like an issue with Phi. The sliding window was 2047, but it's actually supposed to be 2048. Like it might not sound very silly, like, it's just +1, but it actually could affect some fine-tuning runs. So definitely fix that. I'm not sure if they still fix it now, but like essentially they, from what I understand, is like they had like +1 in their code base. So it's 2047 +1 in their code base. But actually in the transformers implementation, they did not actually, copy paste the exact code. And so like the transformers implementation, you must use a power of 2. Well, in this case, a power of 2. It might be like coincidental, but like actually it was 2048. So we verified with the Phi team that it actually is 2048. Yeah. And also like for Phi, you have to like, we noticed that they used a very interesting architecture. So when you do, they fused all the MLP layers, like the MLP weights, and they also fused the QKV into one large matrix. So we found that if you do Lora fine-tuning, you need to actually unfuse them. So you need to unfuse the QKV into like separate 3 matrices. And if you don't do that, your accuracy will be lower than if you fine-tune a unfused model. The reason is because when you fuse the matrices into 3, when you do Lora fine-tuning, your A matrix, so when you do Lora, your A matrix, there'll be only 1. And the B matrix will be fine. But during Lora, you must, like each of the Q, K, and Vs must have separate A matrices. So definitely unfuse them. So chat templates were also a problem that we found. Llama, Mistral, and many other pre-trained models, even like, they all have these issues of tokenizations. Tokenizers are a bit unfortunate for language models. I think like that's probably the biggest issues for language models currently is like tokenizers are like a good temporary fix to like most issues. Like it's relatively hard to get like a piece of text and how do you like chunk them into pieces? You could do it like, like character level. That's probably not a good idea. You could do it like byte level. Or you could use like the current tokenization methods like, BPE and stuff like that. So it's a very good temporary. It's probably not going to be the future. Maybe it's not going to be for the future, but the main issue is because there's so many tokenization problems in current pre-trained models. So for example, on the left, the sun picture is like spaces. So the sun emoji showcases spaces in each tokenization. You can see Llama 2 is like a bit different from Mistral 1. Mistral 2 had like a different tokenization. Mistral 3 had like different ones. And so like the goal is like, which one is correct? Because like if you don't select the correct tokenizer, during the tokenization stage, you could like actually screw up the fine tune. So like definitely you need to like look at the tokenizer, look at which one is the correct one. And yeah, so like there's a lot of issues in tokenizations and chat templates as well. And it gets like more complicated. When you want to export to GGWF has like Llama CPP. Llama CPP has their own tokenization thing. And then so like that also causes even more problems as well. Yeah, so like definitely look at that as well. Yeah, so more tokenization problems. We found, for example, when Llama 3.1 got released, we noticed that the tokenizer did not add a BOS token by default. So this was like a few hours of its release. So we worked with Hugging Face to like add a BOS token by default in Llama 3.1. I think you're supposed to add a BOS token by default. And also like Mistral Nemo also had some untrained token problems. Yeah, and also it was very fun when we were posting these like model analysis on Twitter. You can see both Llama and Mistral that was like packed full of information. Yes, it was very tough in Paint trying to like squeeze everything into the actual model analysis, but it was very fun. Yeah, so now moving on to like bits and bytes. So in Unsloth, we provide Lora, and we make that 2 times faster and use 70% less memory. And the trick is we also have to like consider that, okay, people are going to download the float 16 weights. And we need to like somehow make this process better. And so we decided to like start uploading models to Hugging Face. And so we upload like, for example, pre-quantized bits and bytes models. We upload like GGUFs, and we upload like many models from different model providers. And so like we do this ourselves as well. And so like we find that users, when they use Unsloth, it becomes much easier if we provide our own uploads as well. And also a very big issue that's currently we're trying to solve is when you finish fine-tuning with QLora, you have like the NF4 weights. Like the weights get quantized down to like NF4. It's a data format. And the biggest issue is when you serve these models, we tell people to upcast the NF4 weights to float 16, and then we add in back the Lora weights. There is another method that we know some people do is like they take the actual float 16 weights, and then you add in back the Lora adapters directly, right? So like you don't actually do the upcasting step. We're still investigating which one's better. And there are like 2 methods you could do. We find that maybe the first one might be a bit less ideal. The main reason is during NF4 conversion, there are like some large outliers, which like, language models have like large outliers according to the bits and bytes paper. And so like we find that if you don't, the QLora paper, and so like if you cast it, you might screw up the outliers. And so we find that actually maybe if you do the float 16, just you take the float 16 weights, like the actual untrained float 16 weights, the base model, and just literally add on the Lora adapters, that might actually increase accuracy. So we're going to push that out into Unsloth maybe like in a few weeks. So after fine tuning, we noticed that people have lots of issues with exporting models. So when you do the fine tuning process, that's okay. But then like, how do we actually run the models, after the fine tune process? So we allow people to like run the models in, native transformers. We also like allow people to run the model in VLLM, Llama CPP, OLlama, and more. We found actually that if you use like a Colab, if you save to save tensors, it's actually going to make the saving process 5 times slower. So you have to save to PyTorch bin style. So that was actually very interesting. So this actually made saving like much faster. So we also provide like different quantization methods for people to like push to like Hugging Face as well. And so that was like a very highly requested feature, pushing to Hugging Face, which we also added. We also like allow you to like push multiple quantization methods. For example, like Llama CPP, there's like different precisions, int 8, int 4, and stuff like that. So we allow people to like push different versions of the model to like Hugging Face as well. And we also like work with OLlama to like, now you can like fine tune a model and export it to OLlama and use that on your local computer as well. So we also provide, I think our biggest difference with other training packages is like we actually provide Colabs and Kaggles notebooks to people to use. For example, Llama 3.2, we have a Colab notebook and a Kaggle notebook for people to use. Phi, Gemma. For example, Mistral Small 22 billion actually fits in a Colab, interestingly enough. So 22 billion actually fits exactly in a 16 GB card. So all of these actually fit in 16 GB cards. You can do DPO, you can do ORPO, and many other methods, and these all fit in 16 GB cards. So like our Colab notebooks, we provide all of this to the community, and we also provide Kaggle notebooks as well for people to use. Yeah, so for more code, we actually, interestingly, people were complaining to us that, like when you finish fine tuning, how do you actually run the model inside of Unsloth? We didn't actually have inference type code inside of Unsloth, but I think it was around January or February that we decided to add inference directly inside of Unsloth. So generally, we would suggest people to use Torch.compile now for like faster inference. But in general, when we launched like back in like when we provided inference back in like January or February, this was around 2 times faster than native 4-bit inference inside of transformers. And I think I last checked, it's around 20 to 30% faster than Torch compile still. So like essentially we make the 4-bit inference much faster for people. And we leverage ideas from like page attention. We do like the pre-feeling stage, and then we do the decoding stage separately. So we leverage ideas from VLLM, and we pre-allocate the KV cache as well. So we can do many things. Use Torch in place operations to make it much faster. And so like this was also very interesting. And it's very different from our fine-tuning optimizations. So essentially Unsloth is not just like a fine-tuning faster library. We also have faster inference as well inside of Unsloth as well. We also provide like fine-tuning best practices. So in Unsloth, we noticed that actually you can do continued pre-training. So there was like a paper talking about Lora learns less and forgets less. I'm not sure if you guys saw that, but essentially the paper was trying to say that Lora, if you do Lora, it will forget less than if you do full fine-tuning. We also showed that if you can do 2 times the rank, or like, if you make alpha it's equal to the rank in Lora fine-tuning, this actually can increase accuracy dramatically. And this will essentially allow you to like reach full fine-tuning capabilities if you make the rank go to like all the way to like 4096, for example. So if you make the rank 4096, you have to make alpha also 4096. I think most people, when they did fine-tuning, they would set alpha to 128. So that's actually not good. And so we found that if you set alpha is equal to the rank, you can get much higher accuracies for fine-tuning. We also showed that you can actually do continued pre-training with QLora. Maybe the naming is not very correct, but essentially what you do is we notice that actually, if you actually fine-tune the LM head and the embed tokens, you don't need to fine-tune the layer norm, but if you do that, you can actually mimic full fine-tuning. One of the biggest problems when people do full fine-tuning is they train all the layers, right? Including the LM head, including the embed tokens, RMS layer norm kernels, and they train all of the layers. But in QLora, you don't actually train the LM head and embed tokens. So we show that in some research that we did is like if you train the LM head and the embed tokens, you can actually mimic full fine-tuning as well. But one of the issues is this will actually increase memory usage, so just be careful of that. So in terms of more algorithms that we provided, so one of the biggest things that we did during Lora and QLora fine-tuning was something called chain matrix multiplication. So we showed that actually when you do Lora, you do x times A times B. And actually, the ordering of the x times A times B can actually make a difference in the number of flops that you use. So we showed that actually, if you bracket correctly during the backward pass and forward pass, you can actually reduce actual flops. So this does not reduce actual accuracy. The result of x times A times B, depending on how you bracket, is always going to be like very similar. There's obviously some numerical precision issues, but it's like so small that we just make them the same. And so during the backward pass, we like fuse all the operations. We show that during Lora and QLora, that if you manually fuse all the operations correctly, you can actually make training much faster and also reduce memory usage. So we show through some maths that you can actually show in maths that doing these methods actually makes them much faster as well. We also released something called Unsloth gradient checkpointing, or offloaded gradient checkpointing. We showed that this, I'm not sure when we released this, but this was maybe, I think it was April or something, or March. We showed that if you offload the activations during gradient checkpointing to system RAM asynchronously, you can actually reduce VRAM usage a lot. And actually, this will only increase the training, this will only increase the training runtime by maybe 1 or 3%. So actually, it was a very good, it was reasonably okay to increase the training run, the time spent by 1 to 3%. But I think the benefit was you can reduce VRAM dramatically. We showed that actually, if you use Unsloth gradient checkpointing and other methods, you can actually fine-tune number 70 billion in a 48 GB card. And we're trying to make that go to 40 GB as well, but like essentially you can show that fine-tuning 70 billion, you only need like an RTX A6000, right? You don't need to use H100s. And we also showed that you can actually have 6 times longer context lengths if you use offloaded gradient checkpointing. I think one of the surprise that I found when we talked to people about the gradient checkpointing is like the code wasn't that long. It was reasonably short. And so like you don't need to write that much code to make this happen. But I think it was a bit of a surprise that people didn't actually notice that you can just offload it to like system RAM asynchronously. And this seems to work. So I think the biggest interesting takes was this actually works. And so like, yeah, so I know this is like in many implementations now. Yeah, so like this was like one of our popular type implementation algorithms in Unsloth. We also like we also had to like implement something called chunked cross entropy. When Gemma got released, one of the issues of Gemma was that they increased the vocabulary size to quite large, and so we noticed that actually you can't just use our old cross entropy loss kernel. It does not work anymore. When Gemma got released, you know, like we were trying to like see if we can just use our old kernels, but it actually did not work because the maximum block size for in CUDA was like 6.5. Yeah, it was like 2 to the power of 16. And so you have to actually be careful of that. And so like 65536, I think. And so like so essentially when the vocab size was larger than 2 to the power of 16, we had to like split the kernel into like multiple blocks in order to do them separately. And so we had to like invent like maybe it's in like other kernels, but like we had to like essentially rewrite to the cross entropy loss kernel to account for large vocabulary sizes. And so we called this like chunked cross entropy loss. And so like we do each of the cross entropy loss calculations separately in chunks. And then this essentially also made interestingly, this made it faster as well. And so we also, yeah, so we wrote some kernels for this. We also like wrote this is not a Triton kernel anymore, but like we also did like training completions and training responses. This was actually one of our largest requests that we did not have in Unsloth, was like how do we like mask out the instruction or the input tokens effectively? And one of the biggest issues was we were trying to write like an effective, like a fast implementation of doing this. And we just decided to use pure Python. This seems to work well. So it's around like 2,000 tokens per second. It's not 2,000 iterations per second. So like 2,000 examples per second. So it's reasonably fast. We know other implementations don't do this effectively. They actually have to like tokenize each sentence separately and then like see which sentence, like, okay, is there like a, you know, does this sentence have like a instruction? Does this sentence have like a response? And then they have to do this separately. The trick that we did is you don't need to do that anymore. You can just tokenize in one shot, like just tokenize it, and then we fix the labels afterwards. So that was one interesting thing that we do. We also support like multi-turn conversations. So I think the Hugging Face implementation doesn't yet support multi-turn conversations. So like that's another thing that we provided. It's like this works on like multi-turn conversations, like ShareGPT. Yeah, so like a recent algorithm fix. I don't know if you guys have been following. It's a gradient accumulation fix. So Joey posted like a nice picture showcasing what the issue was. So like as like a story, well, it's really a story, but like generally speaking, the theory was people believed that gradient accumulation was mathematically equivalent to full batch training. So what is gradient accumulation? The trick is gradient accumulation allows you to reduce VRAM usage by chunking up the batch into like smaller components and putting smaller components through the model, through the language model, and you can like essentially get the gradients on the fly, and you can do like in-place addition to the gradients to reduce VRAM usage. But one of the problems that Benjamin posted, so Benjamin was the one who found the bug. Actually, this bug was reported 4 years ago. But we found that actually you have to actually do the denominator correctly. So during the cross-entropy loss kernel, the denominator was actually not correct. And so we showed, so if you see over here, like on the right, the losses was much higher than if you use, full batch training. So during gradient accumulation, so what is gradient accumulation? So on the left-hand side, if you do full batch training, it's actually very simple. You take like, four sequences, you shove it through the network, you get the gradients, and then you do the optimizer step, right? So not that complicated. But the problem is this will use much more memory. So the trick for gradient accumulation is you separate each mini batch into like, steps. You do text 1 first, right? You get the gradients for text 1, and then you go to text 2, you get the gradients. And then the trick is you get the gradients of text 2 and you add the gradients back to text 1, right? So you do in place addition of all the gradients. And then once you do the gradient accumulation, so you accumulate all the gradients, you then do like some math tricks, and then you do the optimizer state. And so gradient accumulation is extremely popular especially for GPU poor people, because this allows you to do mimic full batch training without increasing VRAM usage at all. But one of the problems was, during the cross entropy loss calculation, the denominator was not correctly implemented. So we found that actually, if you do the L2 norm analysis, the difference between fine-tuning on batch size 8, gradient accumulation 2, batch size 4, gradient accumulation 4, and so on. This needs to match up exactly to batch size 16, gradient accumulation 1, right? So because gradient accumulation is supposed to be similar to full batch training, batch size times the gradient accumulation steps must be held constant. And so we found that actually, if you do standard gradient accumulation, the loss, the error actually increases if you use more gradient accumulation steps. And if you fix it, we can then reduce the error to very small. There is still some error though, because when you do accumulation of gradients, there is some precision issues. And so that's the only problem. There are some small little precision issues. But essentially you can reduce the error by a lot if you do this fix. So this is currently already in Hugging Face. So we worked with the Hugging Face team to fix the gradient accumulation bug. And at first, when I posted about it, I thought it wasn't that serious of a problem. Then after we did more experiments, we found that actually it's very problematic. So for example, if you have the gradient accumulation fix on the left, these are the training losses for Llama 3.2. I think it's 3 billion or 1 billion. We showed that on the wiki text dataset, we showed that if you don't add the fix and you do a gradient accumulation steps of 32 and a batch size of 1, the training loss actually goes haywire. It's really bad. And so it's around 1,000 times larger if you do the training losses. And this will actually screw up the training process. And if you do the fix, right, you can get the left-hand side. Right, the right-hand side, the batch size of 32 is the desired actually. So this is actually what you're supposed to get. And if you don't fix it, you will get large training losses. So essentially, the problem was much larger than I expected. And yeah, so we're working with many trainers to fix this issue. So Hugging Face already has this issue, has this fix. Unsloth already has this fix. We know some other trainers have this problem as well, and so we're more than happy to work with them to solve these issues as well. So if you graph out the actual training losses, the gradient accumulation problem is really bad. So this is not scaled. So this is actual loss. And so the red line is the one if you use the broken gradient accumulation. And the yellow line and the blue line are the ones if you use the correct fixes. And also, the blue line is the gradient accumulation if you use gradient accumulation of 32. And the yellow line is if you use just a batch size of 32, right? No gradient accumulation. You can see that the yellow line stops. That's because it was so if you use a batch size of 32, you will get out of memory because you're using the GPU resources to use for batch size of 32 is very large. So the trick is now, instead of using a batch size of 32 and getting ohms, you can use gradient accumulation to mathematically equivalently simulate full batch training. Another one we know that some trainers, what they did is they use unnormalized loss. This also works. So this also removes the gradient accumulation problem. But one of the problems is, the loss goes haywire. So probably don't do that. Yeah, don't provide don't use unnormalized loss in your training runs. This does show that if you do unnormalized loss, if you remove the denominator from the equation, all of the loss curves match up. which is as expected, right? This is correct. But you don't want the, you don't want the cross entropy loss to be like 12,000 or 14,000, right? So like, don't use a normalized loss. Yeah. Yeah, so like we also do collaborations, events, and organization. We collaborate with lots of people. I do have we did like a AI Engineers World Fair talk about low-level technicals of LLMs. It's quite long though. It's like 3 hours. We also we went to the PyTorch conference. That was very fun, talking about making stuff faster. Talking about like LLMs and the future of LLMs as well. And so we also do like collaborations and events and organizations. We like communicate with like the PyTorch team. We're trying to get like Torch AO into like Unsloth. We're trying to get Flex Attention in as well. And we really like collaborating with the entire community. And yeah, so like we have a GitHub package that, please check that out. We provide Colab notebooks. We have like a Discord channel as well if you want to like ask questions and everything. We're on there. And yeah, so so the talk has finished. But thank you a lot for inviting us. So I'm on Twitter, Daniel Hanchen on Twitter. I post a lot about model bug fixes, like making stuff faster. We also have like an official company page called Unsloth AI and my brother. So it's actually kind of like a 2-person team now. So it's just me and my brother still. So if you guys want to have fun on, writing kernels, finding bugs and issues, we're looking for, people to join us on the fun as well. Those are the slides. Thanks a lot.
Sweet. Thank you so much, Daniel. I guess if people have any questions to Daniel, please start typing them in the Q&A. In the meantime, I'll start reading some and ask my own. So there's 2 questions around tokenization, which is why don't people train some tokens for the base model? And can't you basically, Tenisu is also asking, when you're working with an even larger data set, how can we scale a custom tokenization function, which could work best for our specific data?
Yeah, so for the first question, so technically, if I had to give advice to model trainers, yes, for base models, you should train the chat template that you're going to use for the instruct model, because it's more like a user error. It's most people will use the base model and use the chat template that the model providers provide. And so you should train the tokens used for the instruct model inside the actual base model, but it's not necessary. So the main reason why people don't, the model trainers don't train the tokens in the chat template for the base model is because the base model is not for chat, right? It's not an instruct model. And so you don't actually have to train the tokens. So it's not necessary. But as a, for caution for users, we provide a check in Unsloth, but in general, I would suggest maybe the model trainers are okay, maybe just train some of the tokens, make it not 0, right? So one of the issues is just setting it to 0. Maybe a compromise is to set it to the mean. Maybe that's one way, right? Set it to the mean of all the LM head tokens and the embed tokens. I think the second point was about tokenization. Should we do custom tokenizer? Is that the question? Is that the main gist? Custom add tokens back into the model?
Yes, that's my understanding. Yes.
Yeah. So I think we suggest people not to add tokens to the actual fine-tuning run. One of the problems of adding tokens is this will increase memory usage dramatically. If you add tokens, you must train the LM head and the embed tokens, right? So if you do that, now you have to get gradients for you have to upcast float, you have to upcast the LM head and the embed tokens to float 32, and this will dramatically increase VRAM usage. So we don't suggest people to do that. And another problem is this will actually screw up the other. You will actually destroy the model as well. Because this might actually change the behavior of the model by actually changing the distribution of the actual tokens, right? So maybe some of the tokens in the actual instruct model, you're reducing the impact of it. But when you do the gradient updates, you have to update all of the tokens. So maybe don't do that. And so we normally suggest people to don't add tokens to the model, just use the byte back. Because all of these models now use BPE and there is byte level fallback, right? So essentially if you have some new language, just use the tokenizer itself to tokenize it. This will increase, this will not be very efficient, right? You're using more tokens, but in general, I would suggest people not to train more tokens. Yeah.
Got it. So Sam is asking what's the compromise for gradient accumulation? Is there a performance hit? Yeah.
Yeah. So when we first, when Benjamin posted the gradient accumulation problem on Twitter, we like thought it's gonna be that serious. It's not as serious as we thought, but like, at the very beginning, we thought it was not that serious as we thought. But then once we more investigated, like, we worked with Hugging Face to solve the problem, it was actually much more serious than we thought. One of the problems we found is if you do varying sequence lengths, so during fine-tuning runs, there can be very long sequences and there can be very short sequences. Because when you chat with the language model, most people chat with like very short, but some people really use the language model very, like, their chat goes very, very long. And so the main problem we found is during the gradient accumulation problem, long sequence lengths were penalized. We're essentially like, we're underweighting the long sequence conversations and overweighting the short sequence conversations. And so we found that actually maybe this could be one of the reasons why when you do fine tuning on like models, long context fine tuning was not very effective. One of the problems was when people use gradient accumulation, the long sequences were like essentially not even in the fine tuning run. And so like essentially that is why you must fix this issue, especially for long context fine tuning. In terms of like a compromise fix, the only compromise fix that we found was like you can use unnormalized cross entropy loss. That's one way, but this will screw up the fine tuning run. So you need to actually divide the learning rate by like a large amount. And so like probably not a good idea to do it. Yeah.
So I guess what I found interesting about your gradient accumulation bug is like, if I were to compare it to some other bugs you found, like for example, some of the Gemma bugs, those to me seem like a bit more innocuous because like one, there's like how many people are actually downloading the model a few days after the release to then also later fine tune it. And then yes, there's sort of like this thing that's, but this seemed to be like an issue that was like hidden in plain sight. Yet it's like so far reaching that it's kind of easy to imagine it should have been caught a long time ago. So I know there's like maybe some speculation in your answer, but I'm curious if you could speak more to that as well.
Yeah, so I think this was so this is one of our first bug fixes, which is like ever like, it kind of affected many trainers. It wasn't, so this is not just a transformers problem, right? This affected many trainers throughout the entire ecosystem. So this was, the theory was, at the very beginning, was the theory, I think there was a paper that was released in 2017. I think Technium posted about a paper. And so the paper showed that you can use gradient accumulation. Even inside the paper, it was kind of wrong. So they show that, and it's an approximation, you can accumulate the gradients and divide by 1 over the number of gradient accumulation steps. And if you do this, you can kind of approximate full batch training. But the biggest issue was we didn't expect to use gradient accumulation for language models. And sequence models like language models have varying sequence lengths. And that was actually the biggest difference. It's like it was an uncaught bug for like, I think 4 years or something. So some people have reported about this issue on transformers, 4 years ago. And the biggest difference is no one bothered to check that actually, wait a second. Okay, if you do this for like CNNs or like, old style, not old style, like not models that are not language models, this problem is fine, right? There is no problem in like, not language models. But if you do this for language models, the problem exists. And I think people just didn't really bother to check. Wait a second. Like why the error loss, why the error logs not matching? So like I think it wasn't like I think it's more like I think it's when people first wrote the transformer, like, implementation, when people wrote the training code for like other trainers as well, we just took it as like gospel, like, okay, this should be fine. And so like, I think no one bothered to like actually check that actually, wait a second, there is one part of the equation which is like incorrect. So I wouldn't blame this on anyone. It's not really anyone's fault. It's more like just common. It was a common misconception that, gradient accumulation was equivalent, but actually it was not. But now it is, right? So after the fix, actually it is equivalent, right? Mathematically equivalent. Yeah, if that kind of makes sense.
Yeah, it does. Like, I think there seems to be like a lot of value in like writing out the math, and I think you seem to do this like quite a bit to sort of guide the intuition. Okay, so Mark from his iPhone is asking, they're trying to speed up attention for a model. They're not doing anything fancy, no research. Should they stick with flash attention or should they try flux attention?
Yeah, so if you're not doing anything fancy, just use scale.product attention. From, PyTorch does I think for the new PyTorch 2.5 release, they provide, they can use cuDNN's fast implementation. So like definitely use scale dot product attention. If you're not doing anything fancy, probably just use that. Flash attention's fine. The biggest issue with flash attention is the dependency hell. So like when you install it, it's quite complicated too. We find lots of users have problems installing it. That's the problem. So I would suggest people just use scale dot product attention. Flex attention is another very good option. So that's highly suggested as well. So you can also customize the attention mechanism as well inside of flex attention. So definitely do that as well. But if you want like if you don't have any customizations, just use scale dot product attention.
Yeah, like I think I have a pain point near and dear to my heart, which is like building CUDA extensions on multiple Python and CUDA versions and OSs is just like kind of like a lottery. So at least like a big part of what makes this work in the PyTorch CI is we basically build it on everything. Speaking of, is this one of the reasons why, like, because I know you worked at NVIDIA briefly. How
Yes.
come when you were picking up Unsloth, like, because Triton was newer, I guess, and so I'm sort of curious, was building a big part of one of your motivations for using CUDA, or was it more like the user experience for using Triton, or is it more the user experience? So I was curious if you could speak of one to the other.
Yeah, that's a great question. Yeah, so back at NVIDIA, it was fun writing CUDA kernels. So actually, when I joined NVIDIA, I actually did not know how to write CUDA kernels. I knew how to like call cuBLAS operations or like cuSparse operations, but didn't actually know how to write CUDA. So actually, I spent like a few months trying to just learn how to write CUDA. It was painful at the beginning, but I think the learnings that we got from writing CUDA was very important. So like I think there's like a common misconception that like Triton's very easy. It is relatively easy. But I think it's good to have like a CUDA experience before you start writing Triton. And I think we chose Triton. The main reason why we chose Triton was because we were unsure if like NVIDIA GPUs would always be here. So obviously for now it's very common that like NVIDIA is like taking everyone's using NVIDIA GPUs, but we were unsure, right? So could there be like some new hardware or like some AMD or like Intel or like some other new hardware? And so the goal was we selected Triton as like a intermediary method to like not do just CUDA, but like do like a general language for like Triton programming. It's like it compiles down to like all of the other stacks. So like we don't actually have to write like just CUDA code. I think if you write CUDA code, this will still you can get like more speed ups. Like maybe like 10-20% more maybe. But like I think Triton is good enough. We generally rely on like torch compile. We rely on like the Triton teams. They will definitely put all the optimizations back and like make the compiler better. So it's more like a course that we made that it should be good for like future proofing kind of. Yeah. And also it's easy to write in CUDA. Yeah.
Like it sort of makes sense because like I think a lot of the optimizations you really talked about like are also algorithmic in nature. They're not purely systems level optimizations.
Yeah.
And so if you're doing like math, then like sticking to Python seems like an easier choice. All right, so this is more gossip, I guess. Chat is going towards gossip now. So have you been watching the sampling methods that XJDR is exploring with the Entropics code base?
Oh yes, I saw something like this on Twitter. I've not actually explored it, but it's very interesting. I think there was like I think from Opti LLM they posted on Twitter how I think like it still does worse than like chain of thought. I did investigate it a little bit, but I have not really investigated that much. I think I'm gonna do that over the weekend. But yes, I did see it's relatively interesting. It does increase accuracy a lot, so very interesting. That's all I can say. So I'm not the best person to ask about that. Yeah.
All right. So Eric, okay, we have Warren who's saying he's been working on it. Yeah, Warren, if you have any comments, like feel free to post it in chat. Eric again is asking, I haven't really looked at the math yet, but if grad accumulation is not equal to mini batch, do we also get that the expectation of the mini batch is not equal to the full dataset gradient?
Yeah, so okay, there are like I think there are 2 points of the question. I think if you do mini batch training, wait, does the question mean like if you do like full batch, like the whole data set, like actually gradient descent? Or like, okay, okay, maybe I backtrack. Before, when you do gradient accumulation, the theory was it was equivalent to full batch training. So if you use like a batch size of like 128, just a full batch size of 128, the theory was this will be the same as if you use gradient accumulation steps of 128, and batch size of 1. That was the theory. But actually, it's incorrect, right? So like if you use old gradient accumulation methods, this was actually not equivalent to full batch training. So definitely that's not correct. But after the fix, if you actually divide by the correct denominator, actually it is equivalent. Except for like some floating point errors. There is like, we do show there is like floating point accumulation errors of like 0.01, something around there. So there is like an L2 norm of like 0.01. So there is that issue. But if you use float 32, right, if you just use float 32, then gradient after the fix, it is equivalent. But before the fix, it was not equivalent. So I think that's trying to answer the question. I think the other part of the question was like, the difference between actual full batch training, like if you shove the whole data set in, I don't think some people do that. Like, I don't think some people like shove all 1 trillion tokens or like train, like, do like make that as the batch size. I don't think some people would do that. The main reason is mainly like speed. And you're not gonna get any like gradient updates if you like shove in one batch, like the whole batch size. The model probably won't even train that well. So definitely you have to like shrink the batch sizes to like, I think Llama was like 1 million batch size, I think. So yeah, don't use too large batch sizes. Yeah, otherwise your model won't train at all.
Yeah, like for what it's worth, there's like some other hardware vendors, like when I worked at GraphCore, like the research team there was investigating how it's like you get much better convergence if you can do like batch size 1 training. It's just that like on GPUs, that's not a very good choice. I think Jan was sort of like plus oneing some of this work. All right, more questions. Okay, you have a lot of questions, by the way. So RT
Okay,
is
no worries.
asking, are we supposed to use graded accumulation from Hugging Face now if we want to get checkpointing plus 1 dB logging to work in the training args? I never used Unsloth, but are the 1 dB logging and checkpointing in there if I change to Unsloth trainer?
Yeah, so we implemented the fix of Hugging Face a few days ago. So if you install the nightly branch of Hugging Face transformers, the fix should be there. For Unsloth, we provided the fix on day 1. We did not, it was like just pure PyTorch code. So there was no like one to be like logging and like any logging things. There was none. But now so in Unsloth, I think I pushed a commit yesterday to like install the nightly transformers version. And so now there's like logging. So you can now use transformers directly inside of Unsloth as well. So this fix is in nightly transformers. So yeah, no need to like, it's not necessary to use our trainer, but if you want like faster training and stuff like that, we do have to fix internally. I think there are like some issues for so if you just use the transformers code, I think there are like still some issues. So we're still working with the Hugging Face team to fix it. So if you do want like a stable version of gradient accumulation, then just for now you should probably use Unsloth's trainer for now. But I think we're still working with the Hugging Face team to like fix all the issues. Yeah, but it's not just a Hugging Face problem. So if you use like other trainers, I don't know if they're fixed. So do not like, don't like ask me if the train is fixed or not. Like, I don't know. So like I know a lot of people, like, there are a lot and there's a lot of training libraries. And if they all implement gradient accumulation, they will all have this problem. And so like, well, not all trainers, but like most trainers will have this problem. So I'm uncertain if other packages have fixed it. I do know like firsthand that transformers have fixed it. Because we worked with them to fix it. I do not know about other packages. Yeah, obviously Unsloth has a fix as well, but like, yes, I'm unsure about other packages. Yeah.
So Tanish is asking, have you checked Bitnet CPP and what are your thoughts on it?
Yeah, so was this released yesterday? I think it was released yesterday.
Yeah.
Yeah, that's pretty cool. So I think they also released the models, I think as well. So maybe did they ever release the 1.58-bit models? I think I think they also released the models as well together with it. I think the more interesting part was, I think so, or maybe did they release the models before? I'm actually uncertain. Yeah, but I think they
like they didn't release anything you could run up until yesterday, was my understanding.
Yeah,
So this is
exactly.
yeah.
So actually, it was the models. Yeah, it
Yeah.
was more interesting to release the models. I think that was my view. I was like, wait a second, they actually released the models that they like did, the training runs with this 1.58-bit thing. So like, yes, it's very interesting that they released the models. And they did show that actually accuracy is very similar. So like, it's very interesting actually. And I think in general, I think So because this is, I think this is CPU only, right? I haven't actually checked it too much, but this is CPU only for now. Is it correct? Or maybe I'm misrepresenting it. Is it
Yeah,
CPU
yeah,
only?
it's typically
Yeah.
CPU only, yeah.
Yeah. So like I think obviously this would be very interesting if this is GPU as well. But like I think for now, it's relatively complicated to like do it on GPU because like you're not leveraging the I guess you could like maybe upcast it somehow in the tensor-cores, but like it's probably not, it's probably not going to be that effective in GPUs. Maybe if NVIDIA like, adds like support for this in like their newer hardware, maybe. But I would fall back to like Float 4, Float 4 and the new Blackwell chips is very interesting. It could be like an intermediary, like a temporary solution. But I think the 1.58-bit is actually very interesting. You can essentially fit, very large parameter models and like fit this on like CPUs only. And the training losses don't seem that bad. Obviously there is a gap, right? There is a gap between full float 16 training, even float 8 training with the actual 1.58-bit. And we're not exactly sure about the actual true, capabilities of it. Like, we're not like, is this going to be actually that useful for like, for example, long context, long conversation runs? Is this going to be useful? Is it going to like forget some things? We're not sure yet. So I think it's very good for the teams to like release this out to the wild. And so I guess it remains to be seen. I will be trying this out over the weekend as well. So let's see if this is very useful. But I think it is I think the biggest importance was they actually released the model. And so I was actually expecting them not to release the model. So like, why is there such a long, why is this taking so long for them to release the model? Right. So like, and finally they released it. So that was very insightful. Yeah.
So if anyone is interested in pre-training like Bitnet models on GPU, like GoNersT has like an implementation in Torch.io. It's very experimental. We're also not sure how useful it is, but if yeah, again, if you're curious about experimenting, okay, I will take like maybe 3 more questions and then we'll let like Daniel get back to work. So Mark is also asking like, have you seen lolcats and would this be something you're interested in integrating into Unsloth?
Is this the I should probably just check.
It's the linearizing LLMs.
Oh,
So
yes,
basically,
the
yeah.
linearizing attention and oh yes, I remember that one. The one, yeah. I don't maybe someone should put a feature request. I think like we might maybe I'm not exactly sure yet. I think for now we want to like focus on getting more model support. So actually one of our things that is on our roadmap is like making Apple support. We do need help in like Apple support. That's one of the things that we have to have. But like once we get like Apple support done, provide like a UI, do like some extra stuff on like fine tuning, making more vision support. Maybe we'll add maybe that. So maybe someone should like make that as a feature request first. I'll look into it. I think I did like a Twitter post about it. I did not like investigate the package yet, but I think I'll also write that as like a to-do list. So it's a lot to do in the weekend. But I think I did read about it on Twitter. It's actually very interesting, linearizing attention. Think I think my take is I still think attention is still going to be here to stay. I think the trick is attention is like, you can see the entire context in one go. And if you linearize attention, you definitely lose something, right? So like we can't really say what you lose, but I think I like, the experiments show that generally it's fine. But I think in general, I think through, like, for example, on Local Llama, on Reddit, on Twitter, when people try these linearized attention type mechanisms, the quality just seems to be worse in general than full attention. I think the trick, for example, people read the Character AI blog about the, how they did like faster inference. Instead, you should use like, interleaved attention, right? So like 6 sliding window attentions, very small, very, very, very small, sliding window like 2048 or 1024, and then some sort of like large global attention. That seems to work very well. And so like, I think maybe you could like do combination, right? Linearize attention, but then add 1 global attention. Could work. So like, I think you need to add global attention somewhere. And yeah, that's my take.
I think your instinct is correct, and I think even the same lab from Hazy Research like basically later published work saying exactly what you're saying, which is basically you need the global plus the sliding, and that's like will outcompete most sort of like linear attention variants. So maybe I'll ask my own question then here. So something kind of interesting is like you don't have control over how large labs train their models. and they may make certain choices, let's say in training, that makes like fine tuning or inference like slower. And so like one piece of work I'm seeing is sort of like this sort of model surgery, where you like later fine tune a model to recover like some of the accuracy degradations. And I'm wondering if this is like something you've explored, and if not, why not?
Yeah, so is this like, for example, like you quantize, for example, like quantize the weights down to like one bit or 2 bit, and then you train like Q-Lora adapters? Is that
No,
what?
it's more like, for example, you change like the norm pattern from a model, and then you fine tune it to recover the accuracy loss. You change the activations, you
Oh,
change the kind of attention. Like it's sort of like actual model surgery.
interesting. Yeah, so I think there are some people in the Unsloth community who have tried this out. I have not tried this out personally. So like, do you mean like, for example, like changing like squiggly or like
Yes,
glue,
yes,
replacing
yeah.
with like squared red? Okay, probably
Yes,
not squared ReLU, but like ReLU instead, something like
yeah,
that.
yes.
Yeah, that could work. I think if you, so the trick is, I think the trick people do is like there's two ways to like go about it. You can either train Q-Lora, you can train Lora adapters combined with a model. I think someone actually released was that like a few days ago, like someone actually released something about this. They train Lora adapters as well. One of the model releases did something like that. You train Lora adapters together with the actual change that you did to the model, and you can actually recover the accuracy back. This also works for like if you quantize it, if you use torch AOA, for example, right? You quantize it down, and then you use like, for example, Mobius, HQQ, you quantize it down. I didn't torch AOA now, but like, anyways, like if you use torch AOA in general, the accuracy does degrade. But if you train Lora adapters on top of it, you can kind of like recover the accuracy back as well. And so like I think if you do like if you train Lora adapters, if you edit parts of the model, and if you do like continuously fine tune on the model, you can recover the accuracy back. Yeah, I guess it's kind of interesting as well. Like, why does this even work? I think it makes the Lora adapters, I think, makes sense. For me personally, if you like remove, like, if you swap out this swigglue and like replace it with like ReLU, like it doesn't seem like it should work. Like because like you're kind of like truncating all the small numbers to like zero. It kind of doesn't seem to make sense. But I think it could be interesting. Yeah, so I think experiments do show that kind of works. Maybe not all the time. I think like some other things that people do is like they sparsify the network. There are like some research papers which show that if you like if you set like 99% of the small weights to zero, and then if you do that, the accuracy is really, really, really bad. But if you fine tune a Lora adapter on top of this changed model, or you continuously fine tune the model, you could recover back the accuracy. So I think like yeah, so I think it is relatively very interesting that this seems to work still. Yeah.
Yeah, like I guess the way I would understand the intuition you described is like Laura is typically thought of like something to adapt the model to a different task, but you could also think of it as something that adapts a model to basically pretend like it's a different architecture.
Oh
And
yeah.
yeah, and okay, I see. Um,
Yeah, that makes sense. Yeah.
so there's more questions. I'm sorry, Daniel. Like
No
we're gonna
worries.
have the
I have
queue
a
up.
lot of
Okay.
questions. Go ahead.
Okay. So is Unsloth used in federated learning contexts like Poland, HiveMind, Petals, Open Delico style?
You don't think so? So is pedal wait, you mean like distributed learning? Is that I'm not actually not familiar. Is that
Yeah, like I think they mean the actual distributed learning, like the decentralized learning, I guess is what people are referring to here.
Hmm? Wait, what? Can you speak now?
Yes. Sorry, is Daniel
Let
still
me
here?
also unmute. Yes,
Dan
somehow your co-host got removed for some reason.
back? Sorry. I think my
Okay.
died
All right, we're back. Wait, did we
randomly.
both crash? Yeah, sorry, folks.
Oh,
I
it's
will.
funny. Yeah. Anyways, back. What was the question?
Let me see. We're still recording. Yes. Yes. So I think it was about decentralized training.
Oh
Like
yeah,
basically, yeah.
So you could use like, I guess you could use Unsloth on like each device to like make it faster, but I don't think so. We don't have like an orchestration system to like do distributed training. We like, like computer one, computer two, like, do some sort of like communication between them. We don't have that yet. I think Noah's research is working on that. News research, I always get the pronunciations wrong as well. Was it Prime Intellect? They did something like that. So like I think like, yeah, for now we don't support that. But yeah. Yeah, so we don't support that yet.
Yeah.
Future, maybe someone do a feature request as well. Maybe.
This feels like a good community contribution to whoever asked the question. Okay, so maybe the next question again. So from Eric, but like I think this is in reference to the mini batch point. It's like, but the mini batch from theory should be in expectation be the same as the full data set.
Yeah, so that's correct in expectation. So like if you do like large batches in general for pre-training runs, it should be fine. Because like you're essentially smoothing out the denominator across all of the data, so it's generally okay. But for fine-tuning runs, it's definitely not good, right? So like because your batch size is like 32 or like 16 or 128, they're not large, right? Even batch sizes of 1024, they're generally not good. So for smaller runs, this effect is much more pronounced. But I think it definitely needs to be fixed, right? So like in expectation, in the old theory was in expectation, this was good, right? So like, but we show that actually it's not in expectation, it's mathematically equivalent, right? So actually it is the same if you do this correctly, right? So like in order to make it exactly the same, you have to actually divide the denominator. So like essentially this was actually a hidden, like a small little bug that was in all of transformers and all of the trainers, that if you don't actually divide by the correct denominator, you will get, yes, you will only satisfy the in expectation part, right? So like large batches will be fine. But on smaller runs, this effect is much, much, much more problematic. For example, in DPO, especially DPO, for example, right? DPO, people don't use large batches. Generally speaking, DPO, you don't need to use like 1 million batch sizes, right? So like you can use much smaller batch sizes. And so in DPO or like reward modeling or ORPO, this effect is much more problematic. And so like, I think, so after the fix, we show that it's not just an expectation anymore. It is actually equivalent, if that makes sense, yeah.
Okay, absolutely. So Patrick is asking, have you checked DeepSpeak Janus, the unified multimodal understanding and generation?
Yeah, so so interestingly, even the DeepSeek models, we do not support it Unsloth yet, right? The DeepSeek CUDA type models. So that is also remains, I will have to check that as well. For multimodal specifically as well, we're trying to get that out as soon as possible as well. So Llama 3.2 multimodal, that is on our roadmap as well. So maybe next week, I do not know. So yes, another thing that is on our to-do list, if people want to help on contributing that as well, we're kind of like drowning in feature requests now. So like, if anyone wants to help out, that would be much appreciated as well. But yeah, multimodal for Llama 3.2, maybe next week, maybe. Yeah, it's more like, how can we actually fit this into like a T4 GPU? That's the main question. And so like so we're trying to do that as well. Yeah.
Any new suggestions on learning rates depending on model sizes for fine-tuning, or do the older rules of thumb still hold?
That is a great question. I think so the Lora learns less, forgets less paper is very useful. So we collaborated with them. So like they cited some of the methods that we decided, like, said that, okay, you should use like, the rank needs to be equal to the alpha. The learning rate needs to be much larger. So we do show that some of the experiments that they showed is like, you need to use some of the correct presets. I think for fine-tuning runs, we generally tell people to use learning rates of like, 2e minus 4, to 2e minus 5, somewhere around those ranges. I think on pre-training runs, you have to use like much smaller learning rates. But I think for fine-tuning, generally, you don't need to use very small learning rates. Model sizes, I don't think there is that's a very interesting question. So I think maybe the question is like, can smaller models use like different learning rates than like larger models, like Llama 70 billion or Llama 405 billion? That is a great question. I think maybe someone should write a research paper on that. I don't think there's like any research on this. Like, can you fine tune small models and large models with the same learning rate? Maybe the large models you can use a smaller learning rate, maybe a smaller one. And in the small models, you use like a larger learning rate, maybe, or the other way around. I'm actually not sure. Yeah, to be honest, I don't know. Yeah.
Yeah, this very much feels like a run the experiments kind of thing. All right,
Yeah.
so maybe next question from Gecko. Do you think Torch Compile will ever be as good as writing Triton kernels by hand?
That is a good question. I think we chatted to there's like a video of like the Torch. There was like a video we did of, like the Torch team as well. So like I think in general, I think if it's just about fusing, so fusing, Torch compiles fine. So definitely do that. So I would also suggest people to like just use, if you have like a Torch, if you have like have a model, literally like if you just write code in write code in PyTorch, just add Torch compile. Like I don't know why people don't do it, but like just add Torch compile. This makes PyTorch magically faster. I think one of the goals maybe of PyTorch is to make this default maybe somehow. Like allow this to be so stable and so usable that you can just use Torch compile everywhere. So maybe that's one of the goals of PyTorch. I'm not sure. I'm not from PyTorch, so maybe that's one of the goals. But I think the biggest difference though is like for the fusing components, I think for flex attention now, right? So like flex attention does have like some handwritten Triton kernels inside of actual PyTorch, and so that like they use this template to like specialize the template for like different parts. So like that's one thing. I think for other algorithms, there is like a lot of maths involved. There are like, for example, chunked cross entropy was like a thing that we like had to like think about the maths and stuff like that. I think maybe now that might be like placed into Torch compile. But I think there's many other components that do require lots of maths. That's relatively hard for Torch compile to do. But I think Torch compile can get you most of the way there. There's like much more stuff that you have to do for the maths component that's left. Yeah, maybe in the future. Yeah.
I mean, so what you're describing is also very in line. Like, there's like, if people go on Open Review and check the reviews for the Flash Attention 2 paper, reviewer number 2 left an interesting comment, which was like, well, like, why do we need this work? Like, can't compilers just do this? And like, I think Tridau's point was like, no, because like compilers won't like algorithmically change your math and make sure it's numerically equivalent. I guess once humans figure out those tricks, you can always template match them. But like, I don't think compilers are good at novel math. Like, this is actually one area where maybe LLMs are a bit better, but like, I think for now humans are still win. Okay, I'm gonna keep going with more questions. So do you think training Lora on BERT seems like a free lunch, or does that not make sense to do?
Yeah, yes, you could do that. I think some people have actually asked us to support BERT inside of Unsloth. We do not support that yet. So one of the problems of BERT is like, it's encoder style. It's like, it's a bit different from general, like general decoder style models. So we don't support that in Unsloth yet. But yes, I would suggest that, yeah, people could train Loras on that. Yeah, I don't see why not. But I think it's a bit different though. I think it's not different in terms of results. I think the results will be still fine. I think like Lora is not like it's not just for decoder style language models, right? Lora is used in like stable diffusion models. It's using image models. It's used everywhere. So like Lora is like a general technique that can work. Yeah. So I guess yes, you should. Yeah, you should try it out for BERT. Yeah.
Okay, I'm gonna ask you one last big question, and it's a batch of like maybe 5 questions I see in chat. People seem to really like your approach, the way you go about like debugging and testing and talking about your work, and people want to work more with you. And they're trying to figure out like, what does that actually look like? How do I contribute to Unsloth? Like, what kind of research can I do on top of Unsloth to be helpful to the Unsloth community? So where should people engage with you? Can I maybe potentially pitch the server as like one place where you could also do this? So yeah, just like, I guess one mega question for you.
Yeah, definitely. Like, yeah, so we have like a GitHub package. So if anyone wants to like contribute on the GitHub issues, there's a lot of issues. Some of them I have not closed, but there's a lot of issues like feature requests. Yeah, so definitely that's one way to collaborate. We have like a Discord community ourselves on Unsloth. But the GP mode, well, rewrite it to GP mode, but the GP mode server is definitely one place to collaborate as well. I'm also on it as well. So like sometimes I will lurk around. And so like if you want to collaborate on there, that's also another way to collaborate. We also tweet on Twitter. That's another way to. I know people. Unfortunately, some people DM me on Twitter and LinkedIn and email me for like fixing GitHub issues. Please just use the GitHub issues directly. And okay, fine. If you want to escalate the problem, I would respond to them. So if you want to collaborate through those channels, like to be honest, we can collaborate. Like if anyone wants to collaborate, we're like everywhere.
Any public forum, yeah, any public forum.
Yeah, any public forum will always answer. We scour, like we essentially do like daily scouring of like everywhere. So like we'll see your yeah, we're more than happy to collaborate. And we always welcome more contributors. Yeah.
All right. Well, I think that's probably like a good time to end this. Like, Daniel, thank you so much for coming in. Michael, thank you also for being here with us. So for next week, actually for the next 2 lectures, we're gonna have like two lectures on like low bit kernels. So we're gonna have like MobiCham, and then we're gonna have like Lei from the BitBlast team at MSR and at MSR. And so like it's gonna be low bit galore for the next like 2 weeks. So yeah, if you care about efficiency and if you enjoyed this lecture, I'll bet you'll enjoy the ones coming next. And thanks again, Daniel, and thank you, Michael.
Yeah, thanks a lot.
Yeah.
Yeah.